Welcome again to GBS 221. Today we're going to work on the Chapter 3 portion of your textbook on describing data using numeric measures. Remember in Chapter 2 we described data pictorially using the frequency distribution and some of the other charts and graphs that we studied. Now we're going to look at numeric measures, or how to describe that data using numbers. We're going to look at different measures of location, specifically averages. We'll be looking at the arithmetic mean for both a population and a sample. We'll be looking at the weighted mean, which is just another means of calculating both the population and the sample mean. The median, the mode. The textbook will also touch briefly on the geometric mean. However, I won't require you to know that for the homework or for the exam, so you may skip over that portion if you'd like. If you go on to study finance or any finance classes, you may have the opportunity to look at that, and you'll see that it's most closely related to interest rates and whatnot. The first, arithmetic mean, we may look at it from both a population standpoint and a sample standpoint. Obviously, the population simply takes into account all of the items in a population, whereas the sample takes into account only those items in a sample. You'll find the formula for the population mean to be mu is equal to the summation, population mu is equal to the sum of all of the values, or the summation of x, divided by capital N. You can see that on your screen. Mu is equal to the summation of x. Now x is simply all of the items in the population, or that raw data, divided by a capital N. It's a capital N because we're dealing with population. N, capital, population, lowercase, sample. So sum up all of the items and divide by the number of items to get yourself mu, the Greek letter that we used as a variable for population mean. The sample mean is very similar to the population mean. In fact, you could incorrectly use the population formula and come with the right answer for sample. Sample looks the very same, except for now we're dealing with bar x is equal to the summation of x divided by a lowercase n. Okay, so we denote, that is supposed to be a summation, I got a little crazy. We denote sample mean with an x with a bar above it. We call it bar x is equal to, again, the sum of all of the items. This time the x, raw data, refers to the items in the sample, divided by a lowercase n because we're dealing with the sample. So again, you could see that you could incorrectly use either formula in either case and get the same answer, because all you're doing is adding up all of the items and dividing by the number there. However, as we move on to some of the other calculations to describe data, such as standard deviation, if you incorrectly use the wrong one, you'll get the wrong answer. So we want to try to be consistent with our variables and our formula usage from the start. Now, any piece of data, numeric data, that we calculate using population data, we refer to as a parameter. I know it's a little silly, but you can keep them straight by thinking of the same letter. Okay, population, parameter. Any measurable characteristic of a population is a parameter. Whereas any measurable characteristic of a statistic, or when we calculate something, for instance, the mean, the standard deviation, the median, the range, for anything that's sample data, we refer to as a statistic. So again, same letter, sample, statistic, population, parameter. It's kind of a silly way to keep them straight. Now the slides do show you an example of calculating the arithmetic mean. It's a speed study in a neighborhood from that 5 to 6 p.m. hour. On a weekday afternoon, resulting in a following speed data, and you're given a list of data. In order to find the mean, you will sum up all of the items, the summation of x, and divide by n, the total number of items there. There are 11. Now, this is asked then, is this a population or a sample? This is a population because all of the values for that hour were included. There's no indication that we're going to use this hour to infer something about the entire population of all hours of every day. Since there's no additional information given, it reads simply as that we're dealing with a population. Now, properties of the arithmetic mean, whether it be a population or a sample mean, include every set of ratio or interval level data. So those were numeric or quantitative variables, anytime we have interval or ratio level data, we can come up with a mean. All values are included in the mean. Okay, best practice is to include all values in the mean calculation. We talked a little bit about in Chapter 1 when mean isn't the best measure of central location. In the instance of outliers, those values that fall really, really high or really, really low within the data, you'll find that some individuals will choose to throw those out for the mean calculation to make sure they get a more accurate mean, and that's okay to do. Okay, but if you do that, you need to make certain that you document it everywhere that it was done. Because again, best practice is to include all, and if you're going to exclude, you need to explain why. Because also it could look as if you're trying to be biased or providing accurate information in your study. So again, perhaps show the mean with the data and then excluding the outliers. If you can show that it is closer to the median and the mode, you may be able to represent your data then just excluding those outliers. Every set of data only has one mean. Okay, now this sounds a little silly, but once we break it down, it makes more sense. The sum of the deviations of each value from the mean will be 0. Okay? The sum of the deviations of each value from the mean will be 0. What that means is if you take every single original value, take away the mean, the next one, take away the mean, through the entire set of data, you'll have a little column, let's call it, of differences. If you add up that column, it should be 0. The reason for that is the mean is the balance point of the data. It is the value, if you think of it as weight, that falls right in the middle. So if you take away all of the differences, as you add them up, you'll find that you should arrive at 0. Obviously, there's maybe some rounding that goes on, so you may be off by a very, very fraction, but the mean is meant to be, in the absence of rounding, the exact balance point of the data. The sum of all of those deviations should, in fact, be 0. Now, the weighted mean is simply a special type of mean, and I really am not going to belabor it because the reality of it is whether you realize it or not, you're probably using the weighted mean, and I wouldn't require, obviously, especially an online class because I wouldn't see your work, for you to show me that you've used the formula for weighted mean. However, all that it does is take into consideration when you have multiple observations with the same value. And again, I know you do this in your head. If I were to tell you I had 3 people who weighed 100 pounds, 4 people that weighed 200 pounds, and 5 people that weighed 150 pounds, you probably wouldn't say 100 plus 100 plus 100 plus 100 plus 200 plus 200 plus 200 and drag it all out. You'd say to yourself, okay, 4 at 100 pounds, that's 4 times 100, that's 400, plus did I say 5 at 200 pounds? Okay, that's 1,000 plus. So that's all the weighted mean does, is grab the things that are together, multiply it by the number of occurrences. Let me back that up again. Grab the things that match, okay, equal observations, multiply by the number of times they occur, then sum up all of those, then divide still by the total number of occurrences. Again, something that I'm certain that you have done in your lifetime without really maybe referring to it as finding the weighted mean or the weighted average. All right, the median, again, is something that I know you've worked on in the past. The median is simply smack dab in the middle of your data. Okay. Now, the median can be really useful when we are looking at sets of data that have those outliers, really, really high or really, really low values, because they're not affected. Okay, the median is not affected by those. We whittle those away as we move towards the middle. So in an instance of outliers, again, this could be a better measure of central location than the mean if we're going to follow best practice and not remove those outliers. The median is the midpoint of the values once they've been ordered from smallest to largest. I actually have an example coming up, which I'll show you in a minute. Let's step through a couple more things. The median is unique, and there is only one median for each set of values. Median can be used at the ratio level and the interval level, just like the mean, but we could also look at it from an ordinal level, and I'll show you an example of that after the first example with numbers. It is, again, not affected by extremely small or large values. That's why we like it. It also doesn't have to be one of the actual observations. Anytime you're dealing with an even number of observations, you're going to fall on 2 values that lie in the middle. Okay? In order to find the median then, we add those up and divide by 2, or find the average between the 2 that fall in the middle. Obviously, if it's the same observation, no math is required. Let's look at the example. The number of bronze castings produced in a day at Markey Bronze is 87, 62, 91,